All right, so we're at the panel that ends this block, and we'll go ahead and pull our speakers up. The panel is on engineering materials, so I thought along with our technology talks that we'll talk about in materials, they're just as important as the printers. I'll be moderating this panel. We have a really great lineup of researchers, and we're so excited to see what these ladies are doing. So let's get everybody on stage. All right, I think this was everybody. Hello, how are you ladies doing?
Hi. It's really nice to be here.
Is everybody hearing? I think I can hear everybody. We'll just do our mic checks as we go along, I guess. So I will go down the line and let each of you introduce yourself and take a minute or two to talk about your work, your research, and just whatever you'd like to tell us. So we'll start with you, Johanna.
Hi, everybody. My name is Joanna Schwartz. I'm a postdoctoral researcher at Lawrence Livermore National Lab. I'm in the Material Science Division. I'm actually a synthetic organic polymer chemist, but I do a lot of work developing resins and materials for additive manufacturing processes, as well as using chemistries to make new additive manufacturing methods.
Great. All right, Ariel.
My name is Ariel Leonard. I just recently started as assistant professor in the Materials Science and Engineering Department at Ohio State University. Before that, I was a postdoc at the Naval Research Laboratory in Washington, D.C. And so what I'm really interested in is how do we link processing, additive manufacturing processing, to the macro and microstructures that Amy showed earlier in her presentation, to really the deformation and damage behavior. And so a lot of what I do is use pretty unique in situ characterization techniques, whether it's in an electron microscope or it's using high energy diffraction microscopy. I really want to see in real time how the micro and macro structures are developing, and then from there understand how damage evolves because of these macro and microstructures.
Patricia, can you hear me? Oh, we can't hear you. Can you change your mic? Or I don't think you're muted, but your mic is not coming through. So unmute. Yeah, unmute your mic. Okay, well, we'll let Patricia talk to Abby in the chat to troubleshoot her mic problems, but then we'll continue with our other two panelists.
Hello.
Awesome.
Okay, hello everyone and welcome. So my name is Patricia. I'm a doctoral student at the Lappeenranta Lahti University of Technology in Finland. Our research group is dedicated to laser material processing, and I'm working with the laser powder bed additive manufacturing, specifically of metals. So we have in our research specifically worked with two steels, as Finland is basically forest-based industrial sector. These materials, when used, are able to function well under the harsh conditions of the forestry. In the future, the research group is looking into going into Inconel and other magnetic-based metals. One thing that I would say is that my research specifically looks at ways to improve sustainability and circularity of waste materials by way of making separation units in collaboration with the separation department. So for instance, we're making electrodes for gold refinery from waste streams of industries. And this is some of what our research is currently undertaking. Thank you.
Thank you, ladies. All right, so we'll get into our panel. Yeah. So I'm just gonna go in random order here so that we're not just, you know, doing the same order every time. But I wanted to know from each of you, what drew you to additive materials? We'll start with Ariel.
My undergraduate degree is in metallurgical engineering. So I'm really a metallurgist. And I think what really drew me to additive manufacturing, it really allows us to build new fundamental relationships between between processing, structure, and properties, and not materials, but mature systems, like even just standard stainless steel. And it creates these new technologies that can be used for so many different areas. You know, the in situ probing we can do during processing, looking at deformation, looking at how microstructures and macrostructures develop, and how we kind of choose the right processing parameters to get the microstructure that we want. And so it kind of brings life to the metallurgy field. And that really got me excited.
Let's go with you next, Patricia.
Yeah, hello. Thank you for the question. So for me, I started my bachelor's in plastics technology, and then again, it's about recycling, sustainability, saving the world for the future generations. And then I went on to do my master's in design and manufacturing, and that was when I got introduced to the that was around 2013, and I realized that there were a lot I could do with the process, especially in terms with the flexibility, the zero waste, and all the better supply chain systems that the process offered. So I actually got more interested as I learned more about the process, and it offers better means to enhancing the performance of metal components, and especially also because you can use the process or the method to change a lot of properties of materials without actually adding to cost or adding more materials, but rather reducing the materials. So the complexity and the flexibility of the whole process chain is what kind of drew me to laser or additive manufacturing in general.
All right, Johanna.
Yeah, I've always been interested in complex compounds, complex materials, and I think, you know, that led me to Professor A.J. Boydson's group for grad school, which has stimuli-responsive polymers. And so the ability of additive manufacturing to control macrostructure and to then utilize that to control microstructure, stress and strain, and then nanomolecular responses of stimuli-responsive materials across all those length scales, I think is what really got me excited about additive manufacturing, this play between bulk processing and chemical structure all the way through. So I think it's really cool.
Awesome. That's really great. All right. So the next question is, what are some of your favorite materials that you've worked on, and what are their merits and applications? So we'll go with Patricia first.
So the question, please.
Your favorite materials and what are their merits and applications?
Okay. Well, like I said, our research group basically works with tool steels and specifically stainless steel. We're working with EOS M290 currently. That's the latest version of the machine system. And stainless steel 316L, like I said, Finland is forestry-based industry, so more or less you want a material that is sufficient to be able to function well in these harsh conditions, in the acidic, basic, high temperatures. And so that is why majority of the research are in that field. But that notwithstanding, I would say that stainless steel is it has processing properties for the laser powder bed fusion system, so that unlike, let's say, aluminum, which will have some reactivity with the processed gas, stainless steel is very good in terms of the processing stage, and also it has very good rate of atomization, the process for making the powder. So it's one of the metals that effectively can be atomized to get the specific kind of spherical shapes required for laser powder bed fusion systems. Thank you.
I like stainless steel too, and tool steels. Ariel, what are your favorite materials and their applications and merits?
So right now I'm working with an alloy called nickel aluminum bronze. It is an alloy that's usually used in applications where corrosion resistance and both strength and ductility are needed. So ship propellers, underwater fasteners, valves, and pumps. But it's an interesting material because it's what's considered a microstructurally complex and compositionally complex alloy. So it undergoes many phase transformation during solidification, during processing, which makes it pretty cool to study for in additive, because we can avoid certain phases, reduce the ductility or reduce the strength or the corrosion resistance. And so in this material, the things I'm working on really relate to how do we tailor the microstructure and the process to get the microstructure that we want in order to improve the corrosion resistance and the strength and ductility. And so that's been a really cool alloy to work with, just because it's kind of new in the additive space. And so consistently it's been used in a process called wire arc additive manufacturing. And now we're starting to explore it in the powder bed sense. And the reason why is because it's interesting that Trump is one of the sponsors, but they have a green laser system. And what that allows you to do, it's easily or print things like aluminum and copper where the wavelength starts to drop down. So you get lower reflectivity. So in the process, you absorb more of the light, which creates a stable printing process. And so just a lot of cool things in the nickel aluminum bronze system.
Awesome. Sometimes that mic button doesn't turn off when you click it. All right, Johanna, what are your favorite materials and what are their merits?
Yeah, so something I've been, really thankful to be a part of is developing multi-material vat photopolymerization additive manufacturing methods. So utilizing different orthogonal chemistries with different wavelengths, so that color 1 can produce material 1 and color 2 can produce material 2. And so you can get these really complex multi-material objects. The work that I've done so far that's been published is in acrylate and epoxide materials, so radical cationic chemistries, but this ability to, make these same things from a mixed vat of resin and produce these really, hard and soft transitions, hydrophobic, hydrophilic, is really cool to see it form in the vat and actually work. So it's been pretty fun to work with.
Awesome. All right, I'm going to bounce right back to you. You'll be first this time. Let's see. So what are the technical challenges that you face in your research position, in your role? What's really the challenge for you in your research?
Yeah, so I am a material scientist and a chemist in a national lab in a team of, highly interdisciplinary people. And so I really drive a lot of the material choices forward, and that's really exciting, but it's also, a lot of pressure. But then also to correlate, bulk kinetics and material properties to desirable applications, and also relay the importance of those materials to a team that may not have as much chemical background. I think those soft skills of communication and interpersonal, coordination are really important. And so constantly communicating with everyone and sharing results continuously, I think, is both a challenge, but also a really rewarding aspect of working in a national lab.
Awesome. Gotcha. All right, Ariel.
So I think some of my technical challenges is I'm always trying to probe the in situ behavior, so real-time processing. And so a lot of my issues come with data. So you have when you go to the synchrotron, you're collecting many data points. And so how do you process this data? How do you analyze it, especially when you're looking at 4D data basically. And that is definitely a challenge. And so kind of similar to what Johanna's saying, having to communicate with people who are data people, who are into data processing and understand that process and how you get the information that you want out of this data set. That is probably one of the challenges as a material scientist is kind of having to create those teams. And so similar to what she said, the communication, having to learn how to effectively communicate with people who are not material scientists.
Patricia, what are your technical challenges?
Yeah, hello. Thank you once again. For me, as I said, my research is based on sustainability, basically, and trying to communicate the subject of sustainability to somebody who is more used to mechanical, does not really kind of get the meaning. They see it as just a green thing, but it's a concept in design and manufacturing, such that it's about the cost, it's about the efficiency, and it's also about the social impact. So one of the things that I always have to work with or try to emphasize is that when we are talking about design optimization, it's not just about the design, it's also about the material choices, because depending on the material you are choosing, the influence of the laser powder bed fusion. Because if you have a wrong material, your design can be correct, but then the whole thing can be wrong, which can also then affect the functioning and the durability of the component, and as well as the microstructure, as we are talking about, because the layer-wise manufacturing of the component will have not the required functionality as expected if not well planned. If you have a material with low conductivity, which will then sort of not dissipate the heat, then the heat is going to stay in, which is going to affect the microstructure and the properties of the component. So people think sustainability is just about, okay, we want to make something green. But when we come to mechanical department or mechanical topic, the sustainability will make sure that the optimizing of the component is able to be achieved in terms of the design and the material, as well as the manufacturing, for the combined benefits of laser powder bed. I talk about laser powder bed fusion, sorry, because that is where I am mostly working on. So it's additive manufacturing or powder bed fusion based on laser. I think somebody already said electron beam, but this is laser processing. Yeah. Okay, thank you.
Great. All right, moving on to the next question. What expertise do you find is most helpful? Like, is it interdisciplinary? What instruments and techniques? What's kind of the core knowledge and characterization and studies that you do that really help you? Who wants this first? This is a heavy one. Let's see. Ariel, you look primed and ready. I'll call on you.
So for me, a lot of I use are in situ stages, in situ loading frames. And so a lot of the work I do is the synchrotron sources. And so what I'm doing is I want to know for a given, let's say, powder bed stainless steel material that's been processed via laser powder bed fusion. You have porosity, you have residual stresses, you have microstructures that vary. We know, there's orientation relationships between the build direction. So what I want to know is when we're loading it, how do we look at how the pores evolve over time? How do they influence the ductility? How does, plasticity evolve over time? So which orientations begin to share more of the load? What yields first? I want to know how the grain sizes change. So many different things, the grain shape, I should say, morphology, everything is changing all at the same time. And so one of the systems that I use is something called the RAMS. So it's the Rotational Axial and Motion System. It was actually developed by Paul Shade at the Air Force Research Lab. So it's fitted at CHEST, which is the synchrotron source at Cornell, and it's also fitted at the Advanced Photon source at Argonne in Chicago. And so what that allows you to do is while you rotate the specimen, you can also apply a load. It's a camera quite close to it, so you can get the XCT data, so microtomography. You can also get near field data, which allows you to resolve grains and orientation, and there's far field data, so you can get the elastic strain. So that allows you to see which orientations yield. So how is plasticity being shared between different grain orientations. And so that system is very important to a lot of the work that I do because I want to be able to probe all of that at the same time. So that's very different than doing 5 different experiments. I'm actually able to do in one experiment all those things. So I basically get the complete picture of how micro and macro structures are evolving over time. And so that's pretty much a good amount of a system that I heavily rely on. And I would say as far as people, I think I rely heavily on beamline scientists, right? So they know what to do with the detector and the beam that, you know, I have no idea, and it's a learning curve. And so they really are able to push, you know, working with them, they're able to push the beam and the detectors to the limit, again, to get the information that you desire from the experiment. And so I would say those two things are very important for my work.
Awesome. That's so fascinating. And we have follow-up questions about the synchrotron, so we'll get to that in a minute. But Johanna, what expertise do you find is most helpful? What instruments and characterization do you use?
Yeah, so I'm currently working on a new form of additive manufacturing called volumetric additive manufacturing. It's really cool. You can create the whole 3-dimensional structure by essentially displaying a video that of resin, so that volumetric energy accumulates only where the video is present most, right? So you get your 3-dimensional object. And what's really awesome about this is that you can get an object without any layering effects. So it's very similar to its bulk cured counterparts. But the difficulties that arise with, you know, your resin to be viscous enough that your object doesn't sink or float, that your radicals or your chemistries don't diffuse so that you can maintain chemical resolution. But then you also need your optical system to be optically resolved. And then the software you use to create the videos that you display into that vat are also constantly updating. And so this project is, and this work is really interesting to me, but you go from chemical analysis, bulk kinetics, to simulations and software and predictive models as well as feedback, to updating the hardware of the system, which can be mechanical engineers and optical specialists, and then materials testing. And so the iterative fashion of all of those groups and people working together and improving this new method is really fun, but also thereby constantly evolving.
All right, Patricia, what is your key expertise that helps you, and what instruments and techniques do you use? And like,
well, thank you very much for the question. I would say that for me, again, I come to the product design. So basically, I'm working with simulation tools. So sort of performing the FE analysis and the CFDs of the heat transfers of the designs, how the melt pool is going to be moving in the laser powder bed fusion or in the process. So in the sense that when you have the right processing parameters of the process, you will be able to quite then know how the actual to function. I think this has been mentioned already, that simulations help to also cut down costs. And again, I come to sustainability, because when you are able to run these virtual simulations, you can very much tell how much the process, both the material and the laser interaction is going to be, and how the final component is coming out to be. So for instance, in this separation unit I mentioned about the electrodes, we are about multi-materials, whereby we can build the basic form of the electrodes with, let's say, better printable material, which can be stainless steel, and then we can coat the surface with gold films, or is it biomods or something, bismuth or something. Sorry about that. So that is to tell that laser powder bed fusion additive manufacturing allows this traditional manufacturing with the additive manufacturing. So again, we say that it's not manufacturing. This is something we have to say, because most missing the point that additive manufacturing is there to replace traditional, not complemented in terms of the material. Some geometry, but we cannot get it in the traditional. We can get it and face off, enhance the functionality by coating or by any means. So these are some of the things, the interdisciplinary, and some of that I have been working with in my research.
All right, I have one more question, but I'm going to save it to the end. We're going to go ahead and get into audience questions. So if if you in the audience have questions, there's a Q&A tab there in your chat panel. You can just put your question in and upvote the ones that you like. So this very popular question got 6 votes. It says, what are your favorite data crunching programs or languages? And I'm just going to open that up to whoever wants to answer that. Again, what are your favorite data crunching programs and languages?
I'll take part of that. So I would say it depends on what data I'm processing. XCT data, microcomputed tomography. I use a program called IDL. It's really for image processing, and so it really makes it easier to label things like pores or grains, anything like that. So I really use a lot of IDL for that. As far as the fraction data, I use a lot of Python. And so the thing with Python is that I say it's very easy to use because it's Googleable. So if you run into problems, you can Google it, but IDL is not. So it's a bit of a learning curve, and not a lot of people use that language. So if you run into trouble, you kind of have to know the right people to talk to, but it can be quite useful as far as when you're processing images.
Great. Do Johanna or Patricia, do you have any favorite data crunching programs? No is a fine answer. You can just say no.
I get by most of the time with Excel, but Python and MATLAB are both really helpful too. So.
Awesome. All right. What are some little known materials that work wonders in your work? Is that something that you have an answer to? Little known materials. You have some material that you didn't think would work, but ends up working really well, and not many people know about it. It's kind of a very specific question. Nope. All right, we will skip that one. Ariel, you have a question. Can you elaborate on your work with the synchrotron and the 4-dimensional data?
So I talked about it about using this system to probe damage evolution. So using XCT for that, and then using near field diffraction to resolve grains, and how the grain structure changes with loading. So all of this is through looking at loading, and the deformation I'm really interested in is fatigue. So I want to know what happens under cyclic conditions. So what is the cyclic stress strain behavior? What is the fatigue life, which is really what everyone cares about, is what is the life of the component. And so I want to look at how pores affect that, especially in laser powder bed fusion. I want to look at how the microstructure, grain size, morphology, distribution, all of that changes. How does the orientation what are the orientation relationships in reference to plasticity. So again, the RAM system, at the synchrotron sources allows you to do all of those experiments in one. Something else that I've kind of gotten into is the high energy X-ray imaging. And so with these techniques, you can look at pore development during the process, and you can couple that with diffraction, and then you can see what phases are transforming or happening during solidification, which is also very important to the mechanical behavior of the material. So that's a good amount of what I do. And as far as the time resolved, so you can, when you're taking these measurements, you can stop and take a measurement, or you can take it continuously as it's loading. And so that's a big data set, because you have to every point has to match up. And so those experiments are a lot trickier, because it's different than when you're stopping and taking a measurement. You can look at many different, if you think about a stress strain curve, you can look at many points along that stress strain curve. But when you are taking it continuously, you kind of have to be a little bit more specific at what data you're trying to collect. So that's a good amount of what I do. And please email me if you see me at a table, if you want to talk more about the synchrotron work and how it can be useful for you. As of now, you can do powder bed fusion, and you can do DED, in situ probing at a synchrotron source. So very powerful. So again, if you have any questions about that, just let me know.
All right. Which printing processes, such as FDM, powder bed fusion, do you work with most? How do materials change? Technology they work with? I think this is a simple answer. I think you guys have your specific focuses, but I'll let you go ahead and answer, Johanna.
Can you hear me? Yeah. Okay, cool. So yeah, I use mostly photo-based methods or photo-assisted additive manufacturing methods. So that can range from, 2-photon to volumetric additive manufacturing, as well as direct ink write with photocurable resins. And so difference between these, even if you just assume like the same chemistries, like acrylate, free radical acrylate chemistries, the difficulty becomes viscosity differences between these different systems to create still structures that have like toughness or applications that we desire. Things like of the resin, so depth of penetration, or refractive index changes. Can we see the object being formed as it cures? Does it impact the curing of penetration or residual layers? Can it be focused to have a highly resolved microstructure or nanostructure? So it's often playing with chemistries and light to make sure that everything matches on a physical and a kinetic scale.
Go ahead, Ariel.
It depends. It depends on the project. A lot. So for the nickel, aluminum, bronze I talked about, a lot of that is wire arc additive manufacturing, just because you're printing these large scale components. It just depends. When I'm looking at stainless steels, it's a lot of powder bed fusion. The aluminums are powder bed fusion or DED, depending on again what I'm probing. So it varies for me. It depends on the alloy. Right now it's additive manufacturing.
All right, question for Johanna about the volumetric additive manufacturing. I've heard of two groups developing something similar with different approaches, UC Berkeley and University of Michigan. Are you working with one or of these, or is it different?
Yeah, so we work really closely with Berkeley. They call it CAL, computed axial lithography. But basically, I think there's another question about VAM earlier. We use a reverse tomographic approach.
I don't know that.
Oh, sorry, my system is listening to me. We use a reverse tomographic approach. So you can think of it like a CT scan, where you take a look at an object by slicing it at different angles and then putting all those slices together to get intensity of the light energy that you use. And so the video is just an accumulated image of the light energy of that three-dimensional object.
Thank you. Let's see, question for Patricia, and she's I think having technical difficulties. We'll skip those. Let's see, this question I think maybe for Johanna. When you're using a video for creating the dimension of a part, is this using like a hologram or a video information in a 2D that is projected on a surface? I hope you can understand that.
So that's what I was saying about the reverse tomographic approach, where we're essentially displaying a three-dimensional video rotating at an angle at the same rate as the vat of resin is rotating. So you're constantly accumulating energy in that three-dimensional space, and ideally you could cure an object within a single rotation. In practice, it takes more than that.
There she is. Glad to have you back.
Got locked out. I thought everybody was off. Was it just me?
I think it was just you. Sorry.
Really?
Okay.
I'm sorry about that because I'm wondering why am I off?
Oh,
I thought everybody was also off. I'm sorry.
No worries. You have 2 questions though, if you're ready to answer some.
Yeah.
Okay. So the question is, Patricia, what could be some of the major challenges that limit industrial adoption of sustainable materials in manufacturing processes?
Sorry, which limits?
It limits industrial adoption of sustainable materials and processes.
If you say sustainable materials, I don't know what you mean by sustainable materials, because I think laser powder bed fusion additive manufacturing has specific materials that can be used. And I guess it isn't like, okay, we don't use this, we use that. But I would say how you can enhance sustainability with the process is how maybe I would rather kind of speak on. So one thing that we have heard already is that the previous speaker said about 35% of the materials are left as waste. And I have asked the question, or I have said that on the DFAM rules or simulation tools you are going to use in optimizing your design, and then the material choices. And of course, depending on the amount of spatters which are deforming the powder, you will not be able to use this powder again, or then you will need a lot of reconditioning to bring it back to the state of the virgin material to be able to reuse it again. And another thing that I will want to chip in here is that powder bed fusion is not actually going as waste. These metals, if they are big chips, can be used in directed energy deposition in coating of material components. So there isn't really a waste in that sense. And this is something that people must understand, that when we're talking about sustainability in the material chain of powder bed fusion or in additive manufacturing in general, it has to be looked from different dimensions, from the design, from the manufacturing phase, and also about the recyclability of the excess powder, for instance, in powder bed fusion. I guess some of the AM categories do not allow the reuse, because, for instance, if there is a plastic material that is already melted and formed, then there has to be remelting and some other means, which I am not aware of. I wouldn't even talk about that. But I'm talking about powder bed fusion. So, for instance, my first study of sustainability, there were only 5% of metal removed as waste, which could not be reused by mere sieving. But then that is when the topic of directed energy deposition, DED, came up, because then it was seen that these chips can actually be used as feedstock or as input for coating other metal components. So like I said, there isn't like sustainable material, because I wouldn't know what it is sustainable material. But if we're talking about the sustainability of the material chain, then of course, I think this is how I will put it to this question. Thank you.
Great. And I think you also answered the next question. So good job. And then we'll take one more question from the audience, and then I have my final question. So this one's for Johanna. For volumetric printing, are you able to vary the intensity in real time so you could create a single part with different densities?
Yeah, so inherently for volumetric printing, you are varying intensity in part to resolve fine features versus large features or hollow or solid structures. So the way you get contrast of your object versus out of part object is through variations in light intensity. And I believe that this is totally changing the cross-link density and the network formation, particularly in free radical acrylate polymerizations. And so that's really cool. And so normally what we do is we, post cure it to try and mitigate any of those differences. But it could be pretty interesting to use that to our advantage to create, different stiffness structures. And so volumetric is still a really new field. I'm really excited to see all the work that, stems out of this process, and we can start to answer those questions.
And I lied, there's one more question for you. What do you think about the scalability of your technology?
Yeah, so the key limiter, I think, for volumetric additive manufacturing specifically is the optics of the system, right? And, Boeing is already doing things with stereolithography of like giant room-sized vats where they can create these plane wing type structures with epoxies, and it's really cool. But in terms of volumetric specifically, you need that rotation unless you use a holographic approach, and you need co-aligned light. And so I think for something of that scale to go to objects such as personalized medicine or maybe in the dental field, I think that's readily accessible. But to get to larger than that, the next step up, I think is going to require a lot of communication, not only with optics people, but also on the resin scale to make it sustainable and commodifiable.
All right, last question. What excites you about the future of materials for 3D printing? Ariel, we'll start with you. Yes, what excites you about the future of materials for 3D printing?
Yeah, I think with additive, we're able to really explore, I would say, relationships that we haven't been able to explore before, just because, again, the technology that's coming from additive inside the chambers, the way we're able to study damage and deformation and processing and structure, how that evolves during solidification. That's really exciting. And it's not only exciting in novel systems, right, that we're creating, but also these very complex systems that we haven't quite been able to achieve. If you look at nickel, aluminum, bronze, it's not a new material, but the casting of it is how it's been conventionally produced. It creates these microstructures that require a lot of post-processing. And we know with additive, because of these very high cooling rates, we don't get these intermetallic phases that we got before. And so that allows for us to start to further develop those alloys, for different applications. And so I'm excited about that.
Patricia, what excites you about the future of 3D printed materials?
Thank you for the question. I would say that the future of magnetic-based metals that can be printed, it's something that, especially when we are talking about a cooperation with separation units, it will be nice that we can get separation units that can be able to extract these rare earth metals from waste streams and industrial streams waste streams from industries, and then of course be able to reuse them. That the natural resources are depleting, and because of this we need to find ways to sort of reuse what we have used already. But because additive manufacturing is able to make complex parts with better functioning in the separation, in the sense they have higher efficiency, and of course with this lattice, if you know what lattice are, getting the lattice so enhancing this magnetic, or how do I put it? Yes.
Sorry, we're losing you. We're losing you, Patricia. I'm gonna move on to Johanna just to wrap up the panel. Sorry about that. Johanna, what excites you about the future of 3D printed material?
For me, I think, you know, multi-materials is a very large interest to me, and to be able to make these with complex material responses, I think will be really great, including stimuli responsive or smart materials. The idea of programming response into the thing that you make and have it be functional is really exciting. But I'm also really excited by the idea of, you know, what I call advanced manufacturing, this idea of coupling all these different techniques together to create things that, you know, wouldn't be possible otherwise. And so all in all, I'm just excited to see how everything grows and develops together.
Awesome. Well, thank you, ladies, so much. I know I learned a ton. I think this is just a really great panel. So if you guys want to meet the speakers, you can find them in the chat. But we will take a break now and be back in an hour. Thank you so much.
Bye, everyone.
Thanks, everybody.